Okay, continuing on with graphing polar equations. So even though the symmetry helps, so we don't have to spend as much time making our table, it still is a lot of work. So here are some hints. If you have some function f of sine theta, that's always going to be symmetric with respect to the line theta equals pi over 2. And that we would do negative r negative theta to plug in to prove. If your equation is r equals g cos theta, that's going to be symmetric with respect to the polar axis, that's that horizontal axis, and that's our negative theta we'd plug in to prove that it is symmetric. So if we look at the graph, r equals 2 cos 3 theta. Cosine of theta, that's going to be symmetric with respect to the polar axis. That's that horizontal. So again, we only need to find points above that polar axis. And here, oh, that's horrible. So if we look at the graph down here, I'm drawing up the polar axis, which is here, which is why all we need to find are the points from 0 to pi, and then we know the points from pi to 2 pi, we can go ahead and just copy. So just like before, I plug in 0. So this is a little trickier though. So 0 is a nice number. So we have 2 cosine of 3 theta. And theta is going to be 0. So that's 3 times 0. And that's just 2 cosine 0. And cosine of 0 is 1. So it's 2 times 1, which is 2. If we look at, I did a pi over 12. Let's skip that for a second. Actually, let's not. Okay. So 2 cosine 3 times pi over 12. And I keep these in radians. You could change them to degrees if you want to. But if we reduce this, we get 2 cosine pi over 4. Right, because we want 3 pi over 12. And cosine of pi over 4 is root 2 over 2. So we get 2 times root 2 over 2. And these will cancel, and we're just left with root 2. If we did pi over 6, 2 cosine 3 times pi over 6. These reduce, and you get 2 cosine pi over 2. And the cosine of pi over 2 is 0, so 2 times 0 is 0. So you have to do 3 times your angle first, and then whatever new angle that is, that's what you're taking the cosine of. So if we do one more, we'd have to say 2 cosine 3 times pi over 4. So we'd have to figure out what's 3 times pi over 4. Well, that's just 3 pi over 4, or 135 degrees. And the cosine of 3 pi over 4 is negative 2 root 2, negative root 2 over 2. And these cancel, and we're left with negative root 2. So this one's a little bit trickier because it's 3 theta. So 3 times your angle first. Don't do cosine of your angle multiplied by 3. It's 3 times your angle and then the cosine of that total angle. And we'll get our 0 to pi ratio, our 0 to pi r's. So when theta is 0, r is 2. When theta is pi over 12, r is root 2, which is 1.4. When theta is pi over 6, r is 0. R is 0 at the pole or the origin. When theta is pi over 4, r is negative root 2. So instead of being here pi over 4, we got to go down to 5 pi over 4. And that's a root 2, which is a 1.4. When theta is pi over 3, we get r is negative 2. So again, we got to flip it until we get 4 pi over 3, and that's going to be at 2. When theta is 5 pi over 12, r is negative root 2. Again, flip or add 180. I like to think about it as flipping your angle. And that's going to be 17 pi over 12, and with a root 2, which is 1.4. When theta is pi over 2, r is 0. When theta is 7 pi over 12, r is root 2, or 1.4. When r is 2 pi over 3, we get 2. When r is 3 pi over 4, r is root 2. When r is 5 pi over 6, we get 0. When r is 11 pi over 12, we get negative root 2. So we got to go negative over here to 23 pi over 12. And lastly, when theta is pi, we get negative 2, which we already have. Now, if you were to continue this, we would get the exact same numbers. If we did 13 pi over 12, that would be the same as pi over 12. R is negative root 2, so we'd have to go over here to pi over 12 and do root 2, which is 1.4. We already have that point. If you were to continue on between pi to 2 pi, you would see we have already had the points. All the points will be repeated. So now we can go ahead and graph. We can combine all our points. So starting in at 0, we're going to go through these points and come back to 0. And we're going to repeat, go through these points, come back to 0. Same thing down here. This is called a rose pattern. And it has this one has 3 petals because we have cosine 3 theta. It can have more or less petals, but this starts to look like a rose. Okay, moving on. So we have these special types of graphs. The rose always takes this equation, a cos n theta or a sine n theta. It could be sine or cosine, where n is a positive integer, and we're not adding or subtracting anything. It's just a cos theta or a sine theta. And it can have 3 petals. It could have a lot more than 3, but you'll get this looping pattern. Lemniscate is takes the form r squared equals a squared cos 2 theta, or r squared equals a squared sine 2 theta, and that will look like this, just 2 petals directly across from each other in a 180-degree fashion. The limacon, which we saw, takes the form a plus b cos theta or a plus b sine theta, where the number added is a different number than the coefficient in front of the trig function. And these can have a loop inside, or they can have a dimple. The one we graphed earlier, the example we did, had a dimple. What's similar is the cardioid, which is a plus a cos theta or a plus a sine theta. In this case, the number you're adding and the coefficient in front of the trig function are the same. Here the numbers are different. Here the numbers are the same. So very similar between a limacon and a cardioid, but a little different. And lastly, you can get an Archimedes spiral. R equals A theta, where theta is always in radians, and you'll get a spiral that'll just keep going around. Some little tips for the rose curve. There are n petals when your n is odd, and there are 2 n petals when n is even. Right? N is that number in front of your theta. So we just did 2 cosine 3 theta. So 3 was odd, so that's why we had 3 petals. If we did 2 cosine 4 theta, then we're going to have 2 n petals, or 8 petals, because 4 times 2 would be 8, and 4 would be your n here. So that's a little help. Also, the limacons are going to have a loop, right? The loop inside if a over b is less than 1. And back in these equations, if a over b is less than 1, you'll have a loop. You'll have a dimple if a over b is between 1 and 2. So those are just a little helpful hints there. And this will be the end of part 3, and we'll finish up with a shorter part 4 video.